Hey guys! In this video, I'm going to tell you how I used a camera and a laser to make a 3D model of a bench. My target on UMD's campus is right by the Memorial Chapel. Here's my target. It's this lovely bench up by the chapel, and it has a nice curvature to it. You can see from the side, it's very ergonomic, and I just kind of like the shape. From the front, you can see it's a nice semicircle. It's just kind of pleasing to the eye. And then you can see up close, there's this little place where there's a notebook. And people write in that notebook. They can write whatever they want. It's just kind of a fun thing that's on campus. This bench is also cool because it was built by trained inmates at Western Maryland Correctional Institution. And I just think that's a really nice initiative. And then it has this logo. I was curious whether the LiDAR could pick up on the logo. Spoiler alert, it doesn't. The resolution isn't quite that good. What kind of resolution I could get in the slats. But it's also nice because it's by the chapel, so it's pretty. Now I'll tell you how light detection and ranging, also known as LiDAR, works. You have a radiation source, which in my case is going to be a line laser. And then you have a receiver and detector, and I'm going to use a camera with OpenCV image processing. And the light laser will go from the laser source, hit an object, and then hit the receiver and detector after it reflects off. And the Raspberry Pi will be doing the system control and data acquisition. That's all the processing. And then I will use MATLAB for analysis and interpretation. I'm using a nice tripod that I borrowed from Hornbeck Library. And then I have at the bottom the laser, which is the transmitter. I have the Arduino. And then I have the Raspberry Pi, and of course the Pi camera, which is the receiver. And that's 12 inches from the transmitter. And then both of these are being powered from an external battery pack. And I'm using this USB hub to connect both of them to the battery pack. We need to make sure that our laser is aligned with the camera. And we're going to do that by rotating the laser. So you can see it's on the wall. And we're going to use the laser alignment script to help align it. So if you look at that, right now you can see that the green lines are not in line with the red line of the laser. Fortunately, all we have to do to fix that is to rotate the laser in the mount until they're aligned. For this next part, we're going to calibrate the distance of the laser. We have a measuring tape on the floor and the laser set up on the tripod. And we're just going to use a flat wall and measure known distances. Here's the key to the image processing. Even if the object is in the same area relative to the center line of the camera, but one is closer, the closer one will be close to the edge of the camera's frame, whereas the further one will be closer to the center of the camera's field of view. This is how 2D pictures can be used to determine 3D position. And by measuring the known distance, we can determine how what our calibration curve is based on where the laser is. So you can see that when it's closer to the wall, it's further from the center of the camera's frame. So I adjusted the angle offset values until I got ones that looked good for the data, and you can see that the red laser points from my calibration data are well aligned with the blue calibration curve. So now we're ready to go collect data at unknown distances.
Alright, so we're out here, and good thing I brought a flashlight because it's a little hard to see the target, but there's the bench.
So the game plan is to scan up and down the side of the bench, doing a section at a time, and each of these vertical sweeps will consist of probably 25 to 30 photos of the bench. And then once we finish that, we'll go around to the side and we'll do a scan down the back and then up the front of the bench, and we'll repeat that same scanning pattern doing scans across the back of the bench and the other side. The actual data collection process just takes a while. This is sped up to 4 times speed to make it a little more interesting, but I'm moving the laser down 1 degree at a time and taking pictures of the bench.
So I'm out here just to point out a few things that I've noticed about my target that make it difficult. There's a light over there. There's also a light over there, both of which are creating extra noise in that LiDAR equation.
But we can overcome the noise with careful filtering and careful use of the color picker script. Another issue is it was just really cold when I was taking this data, but that's okay. I just put on a lot of layers and it was fine. Another challenge is that the bench I picked is not on level ground, it's on grass, and it's on a bit of a hill. And so that made my data have some weird angles in it that I had to figure out how to overcome. And you can also see there's mulch in the background, and that was very uneven. There was also a tree in the background that got in the way for a little bit of the time. So there are just some environmental factors that made this a little difficult to work with, but I was able to overcome it using data processing. So here's one of the scans that I took. It's of the front right side, and you can see there's a whole series of pictures, and I consider this to be one scan. This is only one of about 20 scans that I took, but I only ended up using about 8 of those scans because there was a lot of noise in some of the scans and they weren't. I used color thresholding to pick out the color of the laser. So you can see that the laser shows up as white and then everything else is masked. And this background, even if it's a similar color, it's not quite right, so it doesn't show up. And then I could use those HSV values to process the rest of the data. And once I have that, I can find the position relative to the center of the frame and plot it in MATLAB. Here are 5 of the front point clouds plotted and stitched together in MATLAB, but it isn't done perfectly yet. And there are some limitations to this. Oops. So if I rotate it, now there's like holes in it, which is a little bit, it looks like there will be some holes in the data, but I think I can also align it better. So when I look at it from this view, this is if we're looking at it from the bottom, and you can see that these are not aligned at like the same angle relative to the camera. So we're going to try to fix that. And if you assume that the camera was at an angle to the bench, then here's the camera's field of view and the bench is projected onto that. So the distances are correct, but the camera is not where we expect it to be. So there's some theta, and if you divide by cosine and sine, you can move this point onto here where it should be. If we had only used a normal rotation matrix instead of reversing this projection, the bench would end up shorter than it is in real life, but using the projection made it the appropriate length. So here you can see the final point cloud. This is a side view, so this is the back side, and then here's like the seat. This is like if you leaned the bench on its back. I'll rotate it around. You can see now we're looking up through the bottom of the bench. I'll try rotating it down a little bit. And there, so that's pretty good. You can see the curve of the back. You can see the little place where the book is stored. And then you can see the 2 different legs. Here's the mesh that I generated in Cloud Compare. And what I did is I first imported my data as a point cloud, which you can see the original point cloud here. And then I created the normals. And you can see they're all kind of showing up as the same color, which means they're facing the same way, and that's good. And the mesh looks pretty good. You can see the curvature of the bench. You can see a little bit of the book. You can see the front, a little bit of the ground. The one thing you can't see too much is the seat didn't have as much data on it, so it didn't really mesh well. And then there's also a bit of a growth on the back I think that's just because the bench is so flat, the curvature was pretty extreme. But overall, I'm pretty happy with how this came out. I think it still resembles a bench and looks pretty good. Thanks so much for watching, and a special thank you to Dr. Mitchell for teaching this class.